Assalamualaikum and hi everyone. This video is about the reaction kinetics, the chapter 1 of SK0 to 5. In this chapter, we will discuss about 3 subtopics. The first one is reaction rate, the second one is collision theory, and the third one is factors affecting reaction rate. But in this video, I just want to focus on 1.1 reaction rate. In these subtopics, there are some terms that you have to know and remember and understand, which are reaction rate, differential rate equation, rate law, order of reaction, half-life, and integrated rate equation. Let's start with reaction rate. It is changes in concentrations of reactants or products as a function of time. For example, I have A produce B. So when I want to calculate the rate of A, I will put the negative sign here to show that concentration A is reducing. So to calculate the rate of A is equal to negative change in concentration of A over change in time. While to calculate rate of formation of B, I will put the positive sign here to show that concentration of B is always increasing. So to calculate the rate of B is positive of change in concentration of B over change in time. Next is about the differential rate equation. It shows the relationship between the rate of disappearance of reactants and formation of products. For example, I have the reaction of 2A produce B. From this balance equation, we can say that 2 moles of A disappear for 1 mole of B that form. Rate of disappearance of A can be written as rate equal to negative 1 over 2 d concentration A over dt. Why I put 1 over 2 here? 2 here is stand for coefficient of A in the balance equation. So it will be negative 1 over 2 dA over dt. Next, rate of formation of B. Rate equal to positive dB over dt. The coefficient for B here is 1, so there is no number to be written here because the coefficient here is 1. As a differential rate equation, I will write it as rate equal to negative half dA over dt equal to positive dB over dt. When you want to write the differential rate equation, don't forget to put the term rate in front of the equation and don't forget to put the symbol of negative or positive. Negative is for reactant while positive is for product. Okay, next term is about the rate law. Rate law is an equation that relates the rate of a reaction to the rate constant and the concentrations of the reactants raised to some powers. For example, I have this equation AA plus BB produce CC plus DD. Small a here are the coefficients for each component in the equation. So, rate law is written as rate equal to K as the rate constant, concentration of A to the power of M times concentration of B to the power of N. Remember, in the rate law, we just include the reactant only. In the rate law, we can have our rate of equation, rate constant, concentration of A with respect to the order, and concentration of B with respect to its order. Since in this reaction I use M and N, we can say that it is M order with respect to A and N order with respect to B. What is the reaction order? The order of reaction shows how the rate affected by the reactant concentration. So it must be determined experimentally. Like as this example, the order of the reaction must be determined experimentally and not the value of coefficient from the balance equation. Okay, now let's look at another example. I have this equation as a balance equation, and the rate law for this reaction, I write it as K concentration of F2 times concentration of Cl2. F2 to the power of 1, ClO2 to the power of 1. How do I get the value 1 and 1 here? They are from experiment value, and it is not the coefficient value from the equation. In this reaction, I can say that this reaction has first order with respect to fluorine gas and first order with respect to ClO2. From the rate law and from the order of reaction with respect to each reactants, we can know the overall order. In this rate law, the overall order is 1 plus 1 equal to 2. Actually, when we already know the units of K of the reaction, we can know the overall reaction order for that reaction. If we have K with the unit of ms to the power of negative 1, it will be zero order. If K has s negative 1, it is first order. What if the unit of K is m negative 1, s negative 1? It has second order reaction. Okay, next, half-life is the time required for the concentration of a reactant to decrease to half of its initial concentration. It is about time. Okay? And lastly, integrated rate equation is the relationship between the concentration of the reactants, which include the initial concentration and final concentration with time and rate constant. So in this syllabus, we only focus on 3 orders of reaction, which is zero order, first order, and second order. Let's look at zero order. So this is the integrated rate equation of zero order that you have to remember because we will apply this in the calculation. So from the integrated rate equation, we can know the T half or half-life of the reaction by substituting the concentration of AT here with concentration of A naught over 2. As half-life, the concentration of a reactant will decrease to half of its initial concentration. Next is first order. This is the equation that you have to remember as first order. Ln A naught over AT equal to KT, or we can rearrange it as ln AT equal to ln A naught minus KT. And we will get our T half equal to ln 2 over K. And the last one that we will discuss in this chapter is about the second order reaction with the integrated rate equation 1 over AT equal to KT plus 1 over A naught, or we can rearrange it as 1 over AT minus 1 over A naught equal to KT, and our T half as 1 over Ka naught. Now let's study about the graph of zero order. The first graph that you have to know is from rate law of zero order, which is rate equal to K. Actually, in this equation, there is A to the power of 0. But since the value of concentration of A to the power of 0 equal to 1, we just can write the rate law for zero order is rate equal to K. So class, for zero order, the rate is independent to concentration of reactant. Or in other words, if you change the concentration of A, the rate is still constant. That's why we get this kind of graph when we plot graph rate versus concentration of A for zero order. Second graph that you have to know is from the integrated rate law. We know that zero order has AT equal to A naught minus KT as integrated rate equation. So, when we plot graph A versus T, you will get straight line with negative slope. Let's have a closer look for this graph. I rearranged the integrated rate equation so that we can relate with y equal to mx plus c. So our y-axis is AT or A, while our x-axis is T. Our y-intercept, C here, is A naught, which is initial concentration. So when we plot graph A versus T, we will have a straight line with negative slope. Alright, this is our half-life, T half first, or first half-life, where at T half, the concentration of reactant will become half from the initial concentration. That's why here I put 1/2 times A naught to show that at this T half, the concentration has become half from the initial concentration. So we will get our T half first from the graph, and we can also get our second T half. Second T half, the concentration has become half from the first T half concentration. That's why it become 1/4 A naught. So from the graph, we can have our second T half. And from the equation of y equal to mx plus c, we can have our slope as our rate constant. Okay, this k is equal to m. So slope here refer to our rate constant. Okay, next we will study about the graph of first order. From rate law of first order, we have rate equal to K concentration of A to the power of 1, as it is first order. So when we plot graph rate versus concentration of A, we will get this kind of graph. Second graph that you have to know is from the integrated rate law. So we know that for our first order, the integrated rate equation is ln AT equal to ln A naught minus KT. But after we rearrange to relate with y equal to mx plus c, we will plot graph ln AT versus T. So the y-axis now is ln A or AT. Our x-axis is T time, and we will have our y-intercept here is ln A naught. Okay, next is graph concentration of A versus T, which it will give curve. Unlike zero order, first order reaction, when we plot graph concentration of A versus T, we will have a curve like this. And this is our A naught, which is at T0. So we have this is as initial concentration. This is our half of concentration from the initial concentration. So we will get our first T half from the graph. We can also have our second T half from the graph. So I label it as T half 2. And from the graph, we can see that the value of T half 1 same as the value of T half 2. This is a significant value for first order reaction, where first half-life is equal to second half-life, x equal to x, thus t half first equal to t half second. We go to the next part, which is graph of second order. From the rate law of second order, which is rate equal to k concentration of A to the power of 2 as it is second order, we will have graph rate versus A as this curve, while rate versus A squared as this straight line. From the integrated rate law, we know that this is our integrated rate equation for second order. We will plot graph 1 over A versus T. So this one that already rearranged the equation so that it can relate with the general equation of straight line y equal to mx plus c, and we will have our slope here as our rate constant. Next, we will look at the graph of concentration of A versus T for the second order reaction. We will also get a curve like first order, but there is some difference with the first order. This is our first T half, where the concentration become half from initial concentration. And this is our second T half. If we look at the graph, we can see that the first T half is equal to x, while the second T half equal to 2x. Means, second T half is double from our first T half. For the second order reaction, second half-life equal to 2 times first half-life, thus T half second equal to 2 T half first. This is the difference between graph of A versus T of second order with first order. Alright, next we will look at some methods to determine order of reaction. We will have 3 methods to determine order of reaction. The first one is initial rate method. The second one is linear graph method. The third one is half-life method. We will start with linear graph method from integrated rate law, as we already learned from our previous discussion. For zero order, we will plot graph A versus T to get our straight line. So, if you have a set of data, concentration of A with time, and you plot the graph of A versus T, so you get a straight line with a negative slope like this, so your order of reaction is zero order. For the first order, when we plot graph ln A versus T, we will get our straight line as integrated rate equation is ln AT equal to ln A naught minus KT. As we discussed before, we will relate with the linear graph equation y equal to mx plus c. So if you have a set of data and after you plot the graph of ln A versus T, you get this kind of graph, means your order of reaction is first order. While for linear graph method, to prove that your reaction is second order is when you plot graph 1 over A versus T. 1 over A versus T, if you get a straight line with positive slope, your reaction is second order. So, this graphical method is called as linear graph method to determine order of reaction. In other words, if you plot graph A versus T, you don't get this kind of graph. Your reaction might be first order or second order. If you plot graph ln A versus T, you don't get this kind of graph, or you get a curve, means your reaction is not the first order reaction. Same goes to this order of reaction. If you plot graph 1 over A versus T, don't give you this kind of graph, means your reaction is not second order. So this is a graphical method. We call it as linear graph method based on the integrated rate equation for each order of reaction. Next, we will study about the half-life method. For this method, we will plot graph concentration of A versus time. Let's look at zero order. As we discussed before, for concentration of A versus T for zero order will give you a straight line with negative slope. For the first order, it will give you a curve where your first T half equal to second T half. And for second order, you will also have a curve, but your first T half is x while your second T half is 2x, where we can conclude that second half-life for second order reaction equal to 2 times first half-life, or we can write it as T half second equal to 2 T half first. So, this kind of graphical method is called as half-life method, and the differences that we get for these all three orders of reaction will determine order of reaction. The last method that we are going to discuss is initial rate method. The first step when using the initial rate method is we use concentration measurement to find initial rate. Second, use initial rates from several experiments to find reaction orders. And the third one, we will use these values to calculate the rate constant. Let's using this example so that you can understand more about the initial rate method. Determine the rate law and calculate the rate constant for the following reaction from the following data. So the question asks you to determine the rate law, and after that it asks you to calculate the rate constant. Two things here that needs you to calculate. And from the question given to you the balance equation and also set of data for 3 experiments. Now we will use our initial rate method. First thing that we have to do is we have to write a general rate law, which rate equal to K concentration of F2 to the power of X times concentration of Cl2 to the power of Y. X here stands for the order of reaction with respect to F2. Y is order of reaction with respect to ClO2. You can also use other alphabets or other unknown, it's okay, but for this calculation, I use X and Y. Okay, next is we have to find order in F2 with ClO2 constant. So first, I want to find the order of F2, which is X. So I have to make sure that the value of ClO2 is constant. And I have to look at the data given. So the value that gives ClO2 as constant value is for experiment 3 and experiment 1. For experiment 3, we have 0.01 and also 0.01 as concentration of ClO2. Then I will substitute all the value into the rate law for experiment 3 and experiment 1. Next step is I can cancel out the value of K, as both experiments will have the same value of K, and also I can cancel out the value of concentration of ClO2. At the end, I will have this kind of calculation, and after all, we will have X equal to 1, which shows that it is first order in fluorine or first order with respect to F2. Okay, next, we have to find order in ClO2. And to find order in ClO2, I have to make sure that concentration of F2 is constant. So if we look at the data, we can see that experiment 2 and experiment 1 will give the constant F2 value or same F2 value. Next, I will substitute into the rate law. And after I cancel out, I will have Y equal to 1, which shows that it is first order in ClO2 or first order with respect to ClO2. Okay, now I already have X value and Y value. Do not leave your answer like this. You have to substitute back into the general rate law that we already write before. So, we substitute X equal to 1 and Y equal to 1 into the rate law. So, we have rate equal to K, concentration of F2 to the power of 1, times concentration of ClO2 to the power of 1. Next, the question asks you to calculate the value of K. You can choose any experiment and substitute the value into the rate equation that we already have before. So in this calculation, I use experiment 1. So I will substitute the value of rate equal to K and concentration of both reactants. I will have K equal to 1.2 M to the power of -1 S to the power of -1. Make sure class, when you write the K value, you have to include the unit of your K. If you don't put the unit of your K, you won't have your final mark for the K value. Okay, that's all for subtopic of 1.1, which is reaction rate. Next topic that we are going to discuss in other session is about the collision theory. Thank you for watching. I hope you can get something from this video. If you have any question, you may leave a comment, consult me or the lecturer immediately.